Welcome back to OK Calculus. This is the second part of a two-part episode. Last time I discussed what derivatives are. I then discussed two rules for finding derivative functions, the power rule and the product rule. If you haven't seen part 1, it is important to watch that first, because I explain each of those subjects in depth. This time, I will continue on the same subject of derivatives. I will go over more rules in finding derivatives. You will learn the quotient rule and the chain rule. Let's first start with the quotient rule for derivatives. This is the general rule for finding the derivative of a quotient. Like I mentioned in part 1, the derivative of a quotient is not equal to the derivative of the top divided by the derivative of the bottom. There is another mnemonic device to use to remember this rule. Just remember the saying, low d high minus high d low, draw a line and square below. The d stands for derivative once again. So basically, you take the bottom, or the low quantity, and multiply it with the derivative of the top or the high quantity. Then subtract the top quantity times the derivative of the low quantity. Divide this by the bottom quantity squared. Now that we know the basics of the quotient rule, let's try it on a real function. Let's try finding the derivative of f of x equals x squared plus 1 divided by 3x. Step 1 would be to take the bottom quantity, which is 3x, and multiply it with the derivative of the top quantity. As you can see, the power rule will be used to find the derivative of x squared plus 1. Bringing the 2 in the exponent out front and dropping the exponent down by 1 will leave you with 2x. The derivative of any constant like 1 is always 0. Now multiply the 3x with the 2x, which gives you a 6x squared. Now on to step 2. We will take the top quantity, which is x squared plus 1, times the derivative of the bottom. The derivative of 3x is 3. Multiplying the 3 and the x squared plus 1 gives you 3x squared plus 3. Step 3 includes taking the results from step 1 and subtracting the results from step 2. Doing this gives us 6x squared minus the quantity 3x squared plus 3. The parentheses are important because you are subtracting the whole quantity. We can simplify this down to 3x squared minus 3. There is one last step, step 4. In this step, you take the results from step 3 and divide it by the bottom quantity squared. The quantity 3x squared equals 9x squared. Our final answer would then be 3x squared minus 3 divided by 9x squared. Once you get the hang of doing this process, it will be much faster. Try one on your own for a minute. Try finding the derivative of f of x equals 2x plus 1 divided by x squared. Pause the video if you wish while you try to solve this. Alright, now that you've tried it yourself, let's do it together. Remember the saying and the 4-step process. X squared times the derivative of 2x plus 1 is 2 equals 2x squared. 2x squared minus 2x plus 1 times the derivative of x squared equals negative 2x squared minus 2x. Divide that by x squared squared, and your answer will be negative 2x squared minus 2x, all divided by x to the 4th. Now let's move on to the chain rule. The chain rule is similar to the power rule, but this time it is a little more intricate. The chain rule is a method for finding the derivative of functions within a function. Take the quantity x cubed plus 2 squared, for example. How would you find the derivative of that? Simple. Use the chain rule. Picture the parentheses and the exponent of 2 as a box, and inside that box is its x cubed plus 2. Logic would tell you that you must open the box first before getting inside. In order to open the box, use the power rule technique. Bring the 2 out front and drop the exponent down by 1. Now that we solved the outside, we must take the derivative of the inside, which ends up being 3x squared. Now you must simply multiply the 3x squared to the 2 times the quantity x cubed plus 2. This simplifies down to 6x to the 5th plus 6x squared. So in essence, you are just taking the derivative of each layer and then multiplying the layers together. The problem may contain more than just 2 layers. I will show you some more examples of the chain rule in our next video. This rule may be confusing right now, but I will clear it up later. There is one more subject of derivatives I must touch on next. This isn't another derivative rule, but it is very essential to know. That important subject would be the derivative of trig functions. You know, like sine x, cosine x, tangent x, etc. Finding the derivative of these is mostly memory. While there are proofs out there done explaining why the derivatives are correct, I will spare you the details and give them to you. The derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. Weird, huh? The derivative for sine and cosine can be charted for easy memory. This chart here shows the derivative as you go down, and then once you hit negative cosine x, the derivative is sine x, and it is an infinite loop. Now on to tangent. The derivative of tangent x is secant squared x. The derivative of cosecant x is negative cosecant x cotangent x. The derivative of secant x is secant x tangent x. And finally, the derivative of cotangent x is negative cosecant squared x. It may seem like a lot coming at you, but memorizing these will help you in the future. Thanks for watching part 2 of my derivatives video. We covered a lot in only a couple of minutes, so next time I will go back and join all of these rules together in our next video. Derivative examples.